In 1887, Hertz discovers the photoelectric effect. And the photoelectric effect, by the way, if you don't remember, says that when light strikes something like a metal, sometimes an electron is ejected. Now, between 1887 and 1905, there were thousands of observations made involving the photoelectric effect. We knew in those 18 years exactly what was going to happen with a certain kind of light. We just couldn't figure out why it happened with a certain kind of light and why it wouldn't. In other words, why electrons were sometimes ejected and why they weren't ejected sometimes. We knew when they would be because we've observed it, but we couldn't figure out why until 1905. In 1905, Einstein introduced this theory that we call photon theory. And basically in 1905, he said, listen, if my photon theory, this theory that says the energy of light is related to the frequency, light exists as a particle, and the energy is related to the frequency and wavelength, will explain the photoelectric effect, okay, will you buy into it? And basically the scientific community said, yeah, okay, that works. Okay, if your theory will explain the photoelectric effect, then your theory must be correct. Your photon theory must be correct. And guess what? It did. It did explain the photoelectric effect, and it explained it beautifully. Einstein's theory basically says this. The energy of a particle of light, or remember what a photon was defined as? A quantum of energy? The energy of a photon is equal to hf or hc over lambda. It's related to the frequency and the wavelength, not how much light you have. So let's use this now. Let's use the observations and use this equation to kind of put it all together and say, yeah, these are the observations, and this is how we explain these observations here. So my first column, you can see, I've got for 4 different things that we do, what's going to happen if that photon is below what Einstein would call the threshold frequency, or that minimum frequency necessary to eject an electron. What happens if we're below the threshold frequency, but we increase the frequency? Still below. We're not increasing it above the threshold frequency, but we're increasing it more than it is right now. What happens? Simple, quick answer to that question. Nothing. Nothing happens. If we're below the threshold frequency, doesn't matter what we do, it's going to be no electrons ejected. What if we increase the wavelength of the EMR when we're below the threshold frequency? What happens? Nothing happens. What if we increase the intensity of the EMR? And the intensity just means more photons. So instead of having 1 flashlight, you have 2 flashlights. Instead of having the light switch on the first dial, it's on the first click on the dial, it's on the second click on the dial. Instead of having a 1.5 volt battery in your light, maybe you have a 9 volt battery in your light. Here we have brighter light, right? More intense light, brighter light. What happens? Nothing. If we're below the threshold frequency, nothing happens. Well, what happens if we take our flashlight or our source of light? We don't increase the intensity of it, but we shine it for a longer period of time, which still corresponds to more photons, right? High intensity, more photons, or shine it for a longer time, that's more photons as well. It's just spread out over time, that's all. What happens now? Nothing. The point that I want to make with this first column is that it doesn't matter what you do. It doesn't matter what you do. If you're below the threshold frequency, or similarly you're above the threshold wavelength, because they both mean the same thing, nothing's going to happen, no matter what. Between 1887 and 1905, lots of people observed that for this type of light, didn't matter what we did, nothing would ever happen. But nobody knew why. Einstein said the reason that nothing will happen is because you're below the certain minimum frequency necessary to eject an electron, and therefore, because frequency is related to energy, you must be below the energy necessary to eject the electron. Now, what happens if we're above the threshold frequency, or similarly below the threshold wavelength? So the threshold frequency is 4 times 10 to the 7, sorry, 4 times 10 to the 14 hertz. We've got 6 times 10 to the 14 hertz. We get an electron ejected, right? A 1-to-1 ratio. But what happens if we increase the frequency even further? So the threshold frequency is at 4. We're at 6, but we increase it to 9. We still get a 1-to-1 ratio, right? But where does that extra frequency go? Well, it goes into extra energy. So if the photon has more frequency, the photon has more energy. And if the photon that's causing the electron has more energy, doesn't mean we get more electrons. It means we get a more energetic electron, right? Okay, if you have a car driving down the road, and that car hits another, or hits an object, let's say a shopping cart in a parking lot. Okay, car's driving in a shopping cart, or in the parking lot, the car hits a shopping cart. If the car has sufficient energy, it will cause that shopping cart to go flying, right? But if you increase the energy of that car, what's going to happen to the shopping cart? It's going to go flying even faster. It's going to be a more energetic shopping cart, right? So if the threshold frequency is 4, then, and we have a frequency of 6, then our car has enough energy to make the shopping cart go flying. But if we increase it to 9, then the car has way more than enough energy to cause the shopping cart to go flying. We still only get one shopping cart go flying, but that shopping cart's going to be moving a lot faster. So what happens here? We have a 1-to-1 ratio, but that electron that's ejected will be more energetic. But I'm going to put a little note to the side here. And Austin's reminded me of this a couple times, that it's still a 1-to-1 ratio. If I have one photon that's way above the threshold frequency, I'll get one electron that's way above the threshold frequency. If I have one photon that's just a little bit above, I'll get one electron that's being ejected. If I have 6 photons just barely above, then I'll get 6 electrons that are just barely ejected. If I have 6 photons that are way above the threshold frequency, then I'll get 6 more energetic electrons that are ejected. All right, what if we increase the wavelength? Increasing the wavelength has what effect on photon energy? Higher wavelength, then lower frequency and lower energy. And if the car that's in the shop or in the parking lot has less energy, we'll still cause the shopping cart to go flying, but the car is less energetic, so the shopping cart will be less energetic as well. So the electron will be less energetic. It's still one shopping cart per car, right? But it's a less energetic shopping cart, or a less energetic electron that's ejected. If you have 15 cars, you get 15 shopping carts go flying. But there'll be 15 less energetic shopping carts because the cars weren't moving as fast. The cars didn't have as much energy. What if we're above the threshold frequency and we increase the number of photons by increasing the intensity? So turn your flashlight on, turn another flashlight on, you got 2 of them now. Okay, brighter light. What's going to happen now? Sorry? You're going to get more electrons, right? This is saying, look, I got one car that's moving fast enough to make a shopping cart go flying. Well, now I got 10 cars that's moving fast enough to make shopping carts go flying. How many shopping carts go flying? 10. What if I increase the time of exposure? So it's not like saying I got 15 cars all at once hitting shopping carts, but rather I've got one car that's got enough energy to move a shopping cart, and then a couple minutes later I've got another one, and then a couple minutes later I've got another one. So total I might have 15, but not all at once. Okay, this is 15 cars all at once with sufficient energy to move shopping carts. This is 15 cars one at a time with sufficient energy to move shopping carts. What's going to happen now? We're still going to get more electrons. It's just going to happen over a longer period of time, right? 15 cars above the minimum frequency will still cause 15 shopping carts to move, or 15 photons above the minimum frequency will still cause 15 electrons to move. It's just not going to happen all at once. We're going to say for all four of these, it's a 1-to-1 ratio. 1 photon will cause 1 electron, 20 photons will cause 20 electrons. 20 photons with more energy will cause 20 electrons with more energy. 1 photon with more energy will cause 1 electron with more energy. Always 1-to-1. Okay? The number of photons affects the number of electrons. The energy of the photon affects the energy of the electron, right? Number affects number, energy affects energy. Got it? Okay, let's deal with this mathematically a little bit here before we do take a look at the work that you were doing yesterday and do a couple more questions here. We know that we have 4 equations that we use with the photoelectric effect. The first equation isn't really unique to the photoelectric effect, but rather it's valid anytime we have a photon. Anytime we have EMR, anytime we have a photon, we're allowed to use this equation. Now, we often associate it with the photoelectric effect because certainly we do a lot of photons within the photoelectric effect, but it's valid at other times too. The next equation that we learned was almost the same. It is unique to the photoelectric effect. The work function, which is the minimum energy, is equal to h times the threshold frequency, which is the minimum frequency. Or we could also say it's hc over lambda max, right? So energy, hf, minimum energy, h times minimum frequency. Next we saw ek is equal to, well, ek max of an electron that's been ejected is equal to 1f mv squared of an electron that's been ejected, right? Kinetic energy is 1f mv squared. But if we apply a potential difference, we can make that electron stop. And the reason we may want to do that is to find the threshold frequency, which you'll see later today or Monday, how we would go about determining the threshold frequency from that, by a graph. But, bottom line is if we stop that electron, that kinetic energy gets converted to something. What's it get converted to? Potential energy, right? Well, it's not gravitational potential energy as the car goes up the hill. Rather, it's electric potential energy. So we'd say Ek is, well, it's 1/2 mv squared, but then as the electron stops, it gets converted to electric potential energy, QV stop. Now, this equation is also unique to the photoelectric effect, but it's not on your data sheet. So I'm going to do this one in red, and I'm going to star it. This one comes from the law of conservation of energy. This one says HF. This is the initial energy that we start with, right? The energy of the light, of the EMR, of the photon that strikes the metal, is equal to Ek max. Well, that's the final energy, the energy that we end with, the electron's energy after it's been ejected. But it's not really equal to each other, actually, because we lose energy in the process. The initial energy is equal to the final plus the energy that we used up in the process. What's the energy that we used up in the process called? The minimum energy necessary to eject an electron, the energy used up in the process, is called the work function. So if we start with 10 joules and we end up with 8 joules, then the energy that's used up in the process of ejecting the electrons must be 2 joules. EI is equal to EF plus whatever we ended up using up. Now, I star this for a couple of reasons. One, because it doesn't appear on our data sheet. And two, because ironically, even though it doesn't appear on our data sheet, it's usually our go-to equation. It's the one that, if we're not sure what to do, that's the one you should go to. In fact, I have a little rule called the 5-second rule here. And it's not the rule that says when you drop something on the floor, if it's less than 5 seconds, you can still eat it. It's a different 5-second rule. Okay, this 5-second rule says if you're solving a photoelectric effect problem, and if you can't figure out what equation to use, after you've got your givens written down, if you can't figure out what equation to use within 5 seconds, then go to this one. because the other equations are simple enough that usually it's pretty straightforward and pretty obvious which one you're going to use if one of them applies. If you can't figure it out, it's probably because it's going to be this equation that you need to use. All right, I want to take a look at I had a couple examples, but first we'll take a look at what you were working on. Example 3 says, the wavelength of EMR incident on a photoelectric surface is 5 times 10 to the minus 7 meters. Now, that's not threshold wavelength. Don't get that mixed up. We're not saying that this is the minimum or maximum wavelength of EMR. This is just the wavelength of EMR. We want to find out what the speed of the electron would be, assuming it's been ejected, if the work function is 0.50 electron volts. Now I'm going to circle that electron volts, even though I don't know for sure if I have to change it or not. I'm going to circle it though because it's not standard. What do we got given to us here? Clearly this is a photoelectric effect problem. Let's write down some givens here. What is this? 5.0 times 10 to the minus 7 meters. What am I going to write beside that? F, lambda, lambda max, E. What is it? Alex, what do we got there? Yeah, that's lambda. Not lambda max, just lambda. We want to find V max, the maximum speed. Now, don't get that mixed up with potential difference, right? It's a small v, not a big V. Work function is 0.50 electron volts. So we're going to say 0.50 EV. What variable is that? E, what is it? Oh, I thought somebody said it there. Is it E? Is it V? Is it... What is it? W. It's not U, it's W. Now we're looking for the speed. That's all we got, I think, isn't it? Who can tell me which equation I'm going to use? Yeah. So Austin just told me, Austin was the only one within 5 seconds that gave me an equation there, and he gave me the right one, the one that I'm going to try here. Nobody else gave me one within 5 seconds, so that means that even if Austin hadn't given me one, we're going to use the one that Austin did end up suggesting, which is the one with the star. HF is equal to EK max plus W. Now, I will say, just like with everything else we do, if you try the wrong one, it's okay, as long as you try something that's valid, and all the photoelectric effect equations are valid. It just means that you're not going to get an answer if you try something else. Now, the reason this one's a little bit trickier to use, and the one that it's a little bit harder to identify, the reason it's a little bit harder to identify is because we often have to do substitutions with this one. In this case, we replace HF with HC over lambda, but they're the same thing, right? HF and HC over lambda. We'll replace EK with 1F mV max squared, but they're the same thing. W, I could replace with HF0 or HC over lambda max, but I don't have to here because I have W. Now, I want to tell you something that I haven't mentioned to you yet. I did say to you earlier on that joules, electron volts, usually you use whatever you want, but there's a couple situations where you have to use joules. As soon as I introduce this or this, I must use joules. If I stuck with this, I'd be okay. Okay, I could still use the electron volts. But as soon as I put in that 1 FMV squared, now I got to use joules. That means I'm going to convert this work function to joules. When I do, it works out to be 8.0 times 10 to the negative 20 joules. Remember how we do that, right? 1 EV over 1.6 times 10 to the minus 19 joules equals X EV or 0.5 EV. Over x. X ends up being 8.0 times 10 to the negative 19. Got to use joules here, which means we got to use joules for Planck's constant, 6.63 times 10 to the minus 34, times the speed of light, 3 times 10 to the 8, divided by the wavelength, which is 5 times 10 to the minus 7. 1/2 of the mass of the electron that's been ejected. And the work function now is 8 times 10 to the minus 20, not 0.5. Let's get the left-hand side. 6.63 times 10 to the minus 34 times 3 times 10 to the 8. Divide that by 5 times 10 to the minus 7. There's the left side. Let's subtract from that 8 times 10 to the minus 20. Let's divide that by 0.5 times 9.11 times 10 to the minus 31, because that's attached to the v squared. And then let's square root that to get v by itself. And when I do, I end up getting 8.35, or 8.4 it should be, times 10 to the, I believe it was 5, 10 to the 5 meters per second. Pretty typical speed for a charged particle. Now, in this equation, you can see if I increase the energy of the photon, then what effect would that have on the electron? It would be more energetic, right? It would be moving faster because the left-hand side would be bigger. Last example of the day, number 4, says the work function is of a particular metal is 4 electron volts. Here's 2 photons. Would they cause emission? Well, what I want to do for this one is to say, like, if the work function is 4 electron volts, like, I got to identify if these photons are above the work function. Let's get the energy of each of these photons. The energy of the first one is HF. I'm going to use the 4.14 value. I can do that because I'm not using 1/2 mv squared or QV, right? So I can stick with the electron volts if I want to. So that gives me an energy. The first photon has an energy of, let's see, 4.14 times 10 to the negative 15 times 9.9 times 10 to the 14 has an energy of 4.1 eV. Is that bigger than the work function?
Yes.
So would electrons be ejected here?
Yes.
Yeah. For every photon you had that had that energy, you get 1 electron that was ejected that would have an energy of 0.1 eV. It'd be a pretty slow-moving electron because we're barely above the work function, but it would still be ejected nonetheless. Let's find the energy of the second one. Here we got the wavelength, so let's use hc over lambda. 4.14 again, times 3 times 10 to the 8. Divide it by lambda, which is 3.5 times 10 to the minus 7. Anybody have that one calculated already? No? Okay, I'll do it then. That gives us an energy of 3.5. Is that bigger than the work function? Nope. Would electrons be ejected? Doesn't matter what happens to this. How many of them we got? Doesn't matter what we do to the frequency or wavelength. As long as we stay under the work function or stay under the threshold frequency, then nothing's going to happen. Yep, Austin? No, we're using 4.14 there. There's 2 values of Planck's constant. There's the one that's 6.63 joule seconds, and then there's the 4.14 electron volt seconds. And since we have our work function in eV, that's what I use in there. Now, if you're confused about whether to use 4.14 or 6.63, what should you do? 6.63. But if you do that, if you use the 6.63 value in here, what do you got to do to this? Convert that to joules. So if you want to go with joules all the time, then it will always work with 0 exceptions. But, like in a question like this, it does sometimes need some extra work. Okay? All right, here's what I want you to do for the next few minutes in class and then this weekend. Worksheet number 20. You've already done the first couple questions. Give you a break. I won't make you do those first 2 questions again, nor will I make you do the last 2 questions on the page. So we're going to make you do worksheet number 20, questions 3 to 13. You're going to find that a number of those questions are going to go very quickly. There's a few of them that are going to take a little bit longer, like that third example that we did.